All right. You guys can hear me? Good. Hopefully you guys had lunch. If you're feeling like a nap, I'll try and help you. If not, you can blame me because. All right. Hey, guys. My name is Arun. I'm one of the founders at Hortonworks. Been working on Hadoop for a long time, about seven and a half years now. I've been working in MapReduce since the beginning, and then I've worked on Tez and now, on Yarn and now on Tez. I'm the SF. I've been, a committer and a PMC member for a long time. I'm also the release manager for 2.0. All right, so, all the boring stuff out of the way. So I'm just going to tell you a story now, right? I promise I'll keep it short, and I'll let Vikas cover the technical details, but there's just a little story about, sort of what Hadoop is and where it landed up and how it landed up where. So there was, Hadoop long ago. 7 years is a long time. And as you guys know, Hadoop had, forever, it's had two major components, right? There's also, to clarify, there's Apache Hadoop, the project, but there's also Apache Hadoop, the ecosystem. What I'm talking now is Apache Hadoop, the project itself, right? So Hadoop's always had, two major components. One is HDFS, right? HDFS allows you to store data, any kind of data at scale, and it's now generally accepted that it's the, sort of the most feasible way to store data at scale and process it, right? So, all right, you got all your data in HDFS by hook or crook, right? And now, what do you do with it? So, MapReduce has been sort of the silver bullet or the big hammer we've used for a long time. And even as we use MapReduce, we've known that it's great for a lot of things. It's great for a lot of use cases. I don't know if you guys know, a lot of Hadoop came because a lot of us at Yahoo at that point were interested in getting web search to work really well, right? And so web search drove a lot of use cases, storage at scale. We were thinking of tens of petabytes at that point. Processing data. In fact, the first large sort of production app we had on top of Hadoop was this thing called WebMap. And WebMap was fascinating in the sense that what WebMap was trying to do was to take every web page in the world, right, model it as a graph, model it as a node in a graph, and take every hyperlink in the world and model it as an edge, right? As you can imagine, that's very interesting for relevance and so on, right? So MapReduce was really great at all these cases. People were really excited. People were really excited that they had a tool which they could run at scale, and they didn't have to worry about things like hardware failures, nodes going down, nodes acting slow, all of these things, right? So this sort of freed up the end user or the developer to focus on the sort of the logic in the application itself. Right? So things were great. But as people took Hadoop and began to do more and more with it, the simplistic model that we had MapReduce on sort of started to act weird, right? So if you think of the entire sort of life cycle of data, right, it's now generally accepted that all your data is sort of going to land up in HDFS. In fact, we at Hortonworks, we've been on record saying that we expect half the world's data on Hadoop in the next 5 years. So if your data ends up in HDFS, you want to be able to sort of interact with it in multiple ways, right? MapReduce is not going to be enough. As an example, as your data comes in from your smartphones, as it comes from your cell phone towers, you want to quickly look for sort of patterns and anti-patterns. You want to look for fraud. You want to look for where your what cell phone towers are dropping packets or whatever it is. So that's sort of what I call event processing. Now, when your data gets on Hadoop, you want to quickly interact. Your data scientists and your data analysts, you want to interact on that data and look for that insight. And once you find the insight, you want to productionize the insight, right? In the sense that you want to run this reporting jobs or ETL jobs every hour, every 12 hours, every 24 hours. You take your pick, right? So if you look at all of these use cases, MapReduce is not particularly great at that. And it just doesn't stop there. Right? Even the algorithms themselves are different, right? If you want to do modeling, MapReduce is not the right way to go, because with MapReduce, you'll have to run multiple jobs, materialize your output HDFS, and so on, right? So there are a lot of demand for things other than MapReduce, as you can imagine. So as we sort of looked at this, I'll probably say around 2007-ish timeframe, it was pretty clear to us that we had to take Hadoop sort of beyond MapReduce, right? And the way we kind of wanted to do was take MapReduce. MapReduce has two different pieces. One is it's got resource management, which nodes are up, which nodes are down, where do I schedule tasks, and then the application itself of running your maps and your introduces. So we split it up into a generic resource management system we call Yarn, right? It's a really bad name. It stands for yet another resource negotiator. We almost succeeded in coming up with the lamest name possible. Almost, right? So what we did was with Yarn, we took MapReduce and just made it one of the applications, right? So MapReduce went from being sort of this be-all and end-all for processing data on Hadoop to become just one application, right? So the key parts of Yarn were we wanted to do things like resource management, utilization, performance, and security, and all these things at a sort of framework level infrastructure, right? So once we did that, we again sort of freed up not the end user, but the sort of the application developer, right? If you want to come up with a cool algorithm, you can now rely on Yarn to do all of this, while you as the developer just focuses on getting your application logic right, or your framework logic right? So if you want to do, let's say, event processing with Storm, right? Bobby and all these guys at Yahoo have got done at this point. They just had to focus on how do you get Storm running how do you get Storm running within the context of Yarn, right? How do you get resources? How do you run your processing application there? You no longer had to worry about, oh, what do I do if a node goes down, right? You didn't have to worry about what happens if I have 20 applications of this kind running, and each of them sort of beat up each other, right? The multitenancy problem. So all of this was sort of Yarn itself. Now, MapReduce, we sort of got there. I would say about 6 to sort of 10 months ago. You've read enough blogs and so on. The Yahoo guys have been doing fantastic work. You got Yarn deployed at extremely large scale, and things are looking good, right? Now, but still, MapReduce was still sort of the king bee in this thing, right, or the queen bee, because things like Pig and Hive and cascading, they're still on top of the MapReduce model, right? The MapReduce model is very simplistic. It's got a bunch of maps and a bunch of reduces. You split your data out, process them in parallel, sort of embarrassingly parallel phase, and then you got one aggregation, right? Now, again, the model itself is not enough, right? We've known for a long while there's been a sort of a cottage industry around writing papers around how MapReduce is the wrong algorithm if you're doing SQL, or if you're doing data flow with Pig and so on, right? So we've known for a long time the same things. So what I've been, and the rest of the team at Hortonworks and lots of people in the community have been working on now, is what we call Tez, right? So Tez is a significantly more general data processing paradigm in which you can run not just MapReduce, but directly translate Pig and Hive down to MapReduce, down to Tez, right? So like I said, MapReduce, if you think of it as an application, it's got a very constrained DAG of tasks it can run. Now, we've known forever that it's not efficient to take a single Hive query and compile it down to 3 or 4 MapReduce jobs. It's not efficient to take a single cascading or a Pig script and compile it down to 3 or 4 MapReduce jobs, right? So what Tez does is it allows us to do all of this within the context of a single application. So the vision is you should be able to take any SQL query or any Pig script and run it as a single job. Does it make sense? So that's sort of what Tez is. And now, now that we've got this done, again, Apache Tez is a project in the incubator at this point. What we've been doing at Hortonworks is we've been taking Hive and getting it down to directly use Tez itself. So in fact, we know Hive no longer needs to use MapReduce, right? And that's a really big difference when it comes to both latency and throughput for Hive queries. In fact, it's not just Hive, it's the same for cascading or Pig. So 2 days ago, well, actually yesterday, we had this Pig developer meetup, and we were amazed to see an intern from Twitter show up and said, oh, I got Pig working natively on Tez. We're like, wow, that's awesome. This open source thing actually works, right? It's really cool to be able to open up these use cases and actually get somebody to validate it for us. So the thing that we are working on now is to take all of these applications, whether it's Pig or Hive, and port them over to Tez, right? We're also clear that Tez is not sort of an end-user application. It's not what we expect MapReduce developers to use or people using MapReduce to use, but it's more for frameworks like Pig and Hive, right? So in some ways, I ran out of cute things to say there. I just wanted to sort of set the context to sort of how we got and where we got, and I'll let Vikas talk about Tez itself, right? Thanks.
Thanks, Arun. Hi, guys. In case you haven't already fallen asleep by now, it's my chance to do it. And so before we start, how did we come up with the name of Tez? Tez is basically a word in the Hindi language which means fast. And so we are trying to say that Tez actually runs very fast. If you run stuff on Tez, it'll run fast. So what it is? It's a distributed execution framework which has been primarily targeted towards data processing applications like Hive, Pig, and other SQL-oriented languages. It's based on the premise that you can express your computation as a data flow graph with a source of data and a sink of data with processing happening in between. It's built on top of Yarn, which is the resource management framework for Hadoop, and it's an open source Apache project, which is Apache licensed. Now let me take you through what the main design goals and design themes of Tez are. This is a very open and interesting topic of research and active development, and possibly it's not possible for us to go through all the details right now. So what we want to leave you with is a taste of why Tez is doing what it's doing and where it is going. So let's look at MapReduce. What was MapReduce doing? It made writing data parallel applications really, really simple. All you had to do was write a mapper, write a reducer, and you're done. Everything is taken care of. Now, while it's easy for you to write a single-page story with that, if you try to write an entire novel, that is, write a really complex application, things get tough because things are hidden from you, and the flexibility that the framework should provide is not there for you to use. And that is why the key design theme for Tez is how can we let the users get all the power that they need from a low-level execution engine so that they can plug in all the user logic at different points where it makes sense. And how can they express their queries in an elegant and natural manner so that they do not have any impedance between what they want to do and how they're actually doing it. The second main design theme for Tez is how do we get performance by design, and how do we enable users and the infrastructure to take advantage of different kinds of performance optimizations at runtime, which are not that easy to get done with MapReduce. So let's look at all of them one by one. Let's take the next theme in empowering end users. Tez defines an expressive DAG definition API with simple APIs like add a vertex to a DAG, add an edge between two vertices, set such and such property on an edge. And using that, you can actually create a fairly complicated graph representation of your computation, such as the graph which is already being shown in that slide. And Tez takes this logical graph and expands it at runtime, adding concurrency, failure control, and all of the resource management so that you don't have to bother about it. You just write your simple logical graph as a set of vertices and edges. This is directly targeted towards query processing applications like Hive and Pig because the optimizers for such languages naturally produce a DAG as an end of their optimization pattern and at the end of their optimization goal. And that maps extremely naturally to the way we have designed the Tez DAG API. Let's take another complicated example. Or if you're doing a completely distributed sort of a totally ordered file. So you take the preprocess stage, which creates samples. That sample is then sent to a sampler stage, which creates ranges for your partition. Those ranges can then get transferred to the partition stage, which partitions the incoming data according to those ranges, which are then fully sorted in the last stage to give you a totally distributed and sorted data. This entire complicated DAG can be expressed using DAG APIs as of now in Tez and can run as a single job. MapReduce had this other constraint that all you could do was map and reduce. But clearly that has fallen short of all the different possible things that users want to do with their actual task runtime, what you are actually going to execute on the machines. So we had to generalize that, and we came up with this input processor output model for our runtime, in which different kinds of inputs are adhering to an input API. The actual compute is adhering to a processor API, and the output is adhering to an output API. And we can construct arbitrary tasks using these different operators. For example, the final stage in a MapReduce job is the operator which is in the middle. And we have created a reduce processor which represents the reduce task. We have created an input called the shuffle input, which takes all the partition data. And there's an HDFS output to write the data out into stable storage. But what if you want to write intermediate data to disk, because it's an intermediate stage in a multi-stage computation? Well, it's simple. You just take the HDFS output out and plug in a file-sorted input, a file-sorted output, and you have an intermediate reduce. What if you want to do a custom join processor in which you have multiple different inputs coming in? Well, you can plug in multiple different inputs to a join processor and plug in a file output processor, and you're done. The key idea here is to have a library of composable operators that can be mixed and matched with each other to perform the desired task according to the computation that you have in mind. And work is still in progress on how we can define annotations on our API so that we know that two operators can actually be composed in a semantically correct manner. We're not yet there, but we want to get there. MapReduce imposed a key value data format to which everybody had to adhere to, even though projects like Hive and Pig use a tuple-oriented or a record-oriented format. Tez is data agnostic. It only concerns itself with transferring the data from the consumer to the producer through multiple layers, and it does not impose any kind of data format on it. So if MapReduce wants to run on Tez, you can use key value. If Hive wants to run on Tez, it can choose to use a tuple-oriented record format. And lastly, we are taking advantage of Yarn's new local resource and data localization APIs to make sure that Tez is really easy for users to consume. There is no deployment whatsoever. There is no downtime to deploy Tez at all. Tez is a complete client-side application. All you need to do is upload Tez to HDFS or any other file system and configure the Tez local configuration to use that, and that's it. What this actually unlocks for you is the potential to run multiple different versions of Tez on the same cluster. So you can run a stable version of Tez for your production jobs, while at the same time you can run an experimental version of Tez for your research and highly advanced users. And both of them will run at the same time in the cluster. However, with great APIs come great responsibilities. Tez is probably not an API which a user will directly code to. It's written for frameworks like Hive, Pig, and other high-level languages so that they do the heavy lifting for the end user, and that is something to be mindful of. We have tried to make the API simple and easy to use, but there is a little bit of a learning curve, and we need to be mindful of that. We come to the next design theme, which is execution performance, and we'll go through the stuff from the easy to the futuristic in the next few slides on what Tez can do and what we wanted to do. Let's look at the straight performance gains that we get over MapReduce because of the simple fact that we are executing an entire DAG of jobs in one shot rather than using multiple different MapReduce jobs. We get rid of the right to replicated stores such as HDFS in between every job. We get rid of launching overhead of the second job. That second job does not need to fight for resources when it is in the queue in the resource scheduler. And we don't need to schedule an extra map task and do the read for the data which in the first place need not have been even written to HDFS. And because of all of these gains, even today, with no further optimization, Tez is faster than MapReduce. And that makes a lot of a difference for small jobs which take maybe order of 30 or 40 seconds to run, because those jobs now have a 2x gain based on our initial results. But let's not stop at that. What else can we do? Since we know the entire plan of the job at the beginning, we can actually work on different runtime optimizations in Tez which enable performance gains to be unlocked. The simplest one is concurrency control. How do you figure out the number of mappers? How do you figure out the number of reducers? Well, Tez can actually figure that out for you at runtime. For example, it can look at the locations of the HDFS blocks and the actual machine allocations that it has been given by Yarn and figure out the right number and location and blocks for the mappers. Let's not stop there. Let's say the map task is finished and Hive had actually told us that it expects 100 partitions to be produced because it expects 100 GBs of output. But Tez found out that there are only 10 GBs of data produced. Well, you don't need 100 reducers for that. You probably can do with 10. And so we reduce the concurrency where it makes sense and avoid using extra resources. Let's take a step further. This is just changing concurrency control. But what if you have to change the nature of your graph itself at runtime? For example, 10 levels down in your job, you have to join between A, B, C, and D tables. Now, the join order over here is very important, right? It may make a lot of difference in performance whether you do join A, join B, followed by join with C, followed by join with D, or you do it the reverse way, C, join D, followed by B and A. These kind of dynamic reconfigurations of plan, either by Tez independently or in concert with the user level optimizer or a Hive plugin into the Tez AM, is definitely part of the design of Tez as we have written it as of now. It doesn't work, but it will soon in a couple of months. What about resource management? Getting containers and getting resources in a distributed system is expensive. It takes time, and you have to get good use of it. So that is why reusing containers to run your tasks and having the ability to host shared objects within that reusable container is important. For example, for iterative queries where the shared memory can be reused between different iterations and different stages. So Tez as a task host, so there's a Tez task host which actually invokes the user code, and it has the capability of actually running more than one task one after the other as tasks complete. And that gains anywhere between 2 to 5 seconds of task launch time in between multiple stages. And this is the really futuristic one, but something that is not really that far off, which is, since Tez has a lot to do with the physical movement of bytes, how can we optimize that so that we are doing the best that we can at any given point of time? For example, let's say the initial plan was that the producer writes a local file for their intermediate outputs, and then it's consumed by the next stage. What if Tez finds out that the outputs produced are not really that high? So do we really need to spill to disk? Probably not. We can actually use an instance of RAMFS or some other memory store that we have on that node to store that data. Let's say that there is a graph in which there are two stages which have a streaming edge between them such that the producer is actually streaming data to the consumer. If Tez manages to co-schedule those two tasks on two different machines, then it can choose to use an over-the-network streaming operator. But if it can actually co-schedule them on the same machine, then it can possibly choose to use an in-memory streaming operator. And that is where the pluggable input-output processor model of Tez comes handy, because you can plug out a network streaming operator and plug in an in-memory streaming operator. So with all this said and done, what is the current status? So Tez is currently an Apache incubator project, and it's under rapid development for over 3 or 4 months. Over 270 JIRAs have been filed, and over 170 of them have been resolved. And there's a growing community of folks from Hortonworks, Microsoft, and even Twitter who are starting to contribute to the project. But despite all this rapid development, we have a laser focus on stability and making sure that all the code is well tested and stable. I just ran code coverage numbers last night, and for all the new code that we've added, we already have over 70% code coverage. And it's ready to be deployed. In fact, we have deployed on multi-node environments and run it at scale. What is working functionally? Tez can currently execute map and reduce tasks as map processors and reduce processors. Now, that's also a pragmatic decision because, to be frank, there is no other viable runtime for the framework right now. And multiple man-years of effort have actually been spent in writing all the different libraries of mappers and reducers that different organizations have written, and we possibly can't throw all of that away. So we will leverage all of them, and that's why we've written a map processor and a reduce processor to wrap around map and reduce. And using that, today you can actually run any MapReduce job on top of Tez with little or no modification as is. In addition, Tez has the ability right now, as of today, to run a complete DAG of MapReduce processors. So you can create an arbitrary tag of MapReduce operators, and Tez will be able to run it for you as a single job. There is a working prototype of Hive, which is using Tez as the targeted runtime. Work has already started, like Arun mentioned, on a prototype of Pig, which also targets Tez as the runtime environment. We're already seeing promising performance numbers based on those. So what is the USP? This one slide tries to capture the USP that Tez is proposing. This is a very common pattern of multiple series of joins happening, which is typical in most of the TP-CDS benchmark queries. And let's say the optimizer is really smart and the data sizes are really small, and it can optimize this job into a single start join and run it as a single MR job. Well, you can run it as a single Tez job also. But what if you can't, and you have to run it as a multiple sequence of operations? Well, again, you can run that same job in its different format as a single Tez job. So whether you're running a short, small query or a large, bad job, both can run on Tez as a single job on the same framework. Looking ahead, we obviously have to finish some of those performance optimizations so that we can take advantage of them. But as of now, we are definitely looking for early adopters and contributors, because as we flesh out the design aspects of Tez and before they get solidified, we need as many user cases and as many user stories as possible so that we can incorporate them into our design so that we know that we have all our bases covered. And at the same time, we need a growing contributor community so that all of those dreams can actually materialize into working code. So please stay tuned for Tez meetups. We'll have a link out soon, and there we hope to have really deep dives into the architecture design of Tez and how you can use Tez either as an application developer or a user or as a contributor. There are a bunch of links over there for the Apache Jira site, the GitHub site. There is a high-level design document and API specification, which is already available on the third link saying Tez 65. We have a bunch of developer lists, which I would encourage interested people to subscribe to. A lot has been said, and probably this is that time of the afternoon when the lunch is getting to our heads and you're feeling a little doozy and sleepy. But even if we've ignored all of these slides, what are the takeaways that we want you to go away with? One, Tez is a distributed execution framework that works on computation that is represented as a dataflow graph. It naturally maps to execution plans produced by query optimizers and is a natural fit for them. The architecture has been designed from the ground up to allow dynamic performance optimizations at runtime. It's an open source Apache project. Your use cases and your code are welcome. It works, and it is already being used by consumers like Hive. Thanks for your time, and we're open for questions.
What time scale are you guys targeting? Seconds, hundreds of milliseconds, minutes?
So can you repeat that? I wasn't quite clear which time scale you're talking about.
What time scale are your, for example, Hive on Tez queries? Or what are the fastest Hive queries that you can currently run?
So what we've done now is we've gotten, well, again, well, we definitely don't want to oversell, one piece of technology, right? So Hive is a complex piece of software. It's SQL in Hadoop, right? So with a lot of work, including work on the Hive optimizer itself, the Hive optimizer in Hive 10, for example, would not do a good job with star joins, right? Even if things fit in memory, it would not put in memory. So we fixed that, of course, in Hive. And then we obviously used Tez itself. So we've gotten queries down from 1,800 seconds down to 30 seconds or so at this point. We've also done other pieces of work in Hive where, so you guys should definitely go to Alan's talk on Hive. So he'll talk about vectorization. With vectorization, we've got queries down from, again, tens of seconds to 16, 18 seconds. And we're just sort of getting started. One of the things we haven't talked about is we're adding this notion of a Tez service. So it'll be pre-bombed containers of Tez running all the time. So you can take a query and distribute it out. So there, you completely do away with the startup cost. We measure the startup cost. We know the startup cost. We're paying about 5 seconds overhead. We can easily eliminate that and go down under 10 seconds or so. So a combination of factors. It's not just Tez, but increasingly you'll see us do more and more. Actually, the interesting part about Tez is it's not just at the lower end of the spectrum. It's also if you go to the higher end of the spectrum, you've got a 10 terabyte fact table join with a 10 terabyte fact table join. Hive itself makes a significant, Tez itself then starts to make a significant difference because you're now no longer going to HDFS for your intermediate outputs, right? That makes a huge difference. And over time, you'll see us add things like, we already have a prototype of an in-memory shuffle. So we'll never hit disk. Other than the initial input and the final output, we never hit disk in between completely. So a combination of this gets a lot of bang for the buck.
Second and last question. I didn't quite catch, is Hive on Tez available now, or is it?
Yeah, so there is definitely patches. There's a branch in the community. We just released a Hortonworks data platform too. So if you download, you get the integrated version. There's a switch you need to flip which says run Hive on Tez or run on MR. Both of them are available. You flip the switch, you get the right runtime.
So I got the impression that Tez was the way to run MapReduce over Yarn. Did I misunderstand you, or?
Eventually. Today we have both runtimes. We have the MapReduce runtime and the Tez runtime. Over time, you can
MapReduce over Yarn?
Yeah, MapReduce over Yarn, Tez over Yarn. Okay. Both of them are two different runtimes.
Okay.
You'll see us get to a point, I don't know when, but we don't really need, since Tez is a significantly more general runtime than MapReduce, it's easy to run MapReduce applications on Tez.
So MapReduce is what? It's a complete bipartite connection between two stages, and you can express that in Tez as a very simple use case of Tez. And so, as of today, you can actually run that kind of a graph on the Tez runtime. All you need to do is flip a configuration in your Yarn, in your MapReduce configuration to say, instead of using MapReduce, use Tez as the runtime, and your existing MapReduce job will just run on Tez.
Thank you.
I have a question about the task reliability. For MapReduce, since each map and reduce task is persistent to either local disk or other output, so when a single task is failed, then it can be re-executed elsewhere. So for Tez, it's executed as a DAG, and there are no intermediate persistent. So how the data is secured, or when a single task or a single stage is failed?
So Tez continues to have options. You can so the base one we implemented was it does have persistence on disk. Yeah. So the intermediate output is persistent local disk, but not to HDFS. So we can roll back on failures and give you the same semantics you have on MapReduce. But also Hive has the option to not have that, and a higher level application like Hive can pick it. It says, do I want to persist this data or not? Right? If it doesn't persist, it has to deal with. We can deal with failures too. It just will be. Failures will be more expensive. So the optimizer on top, which is Hive or Pig, they get to make the choice of what kind of fault tolerance they want for their tests. Both are available.
It kind of boils down to the spectrum of jobs that you run, right? For longer running jobs, you can afford to spill to disk. In fact, if it's an extremely long running job at distinct points in the job life cycle, you actually would want to check point to HDFS so that you don't have to rerun a whole series of tasks just because you lost a bunch of machines. But then, if you're running a very short task, very short job, which is supposed to finish in the order of seconds, then probably you don't want to spill to disk, and rerunning the entire job if there is a failure may even make sense.
So you can make that choice at every stage in the tag.
Okay, you mean that Tez have the flexibility and
yeah.
let user control it?
Yes.
Well, again, when I say user, it's not end user, it's Hive.
I mean the Hive
or Pig.
Any developer to write the test.
Sure.
Correct.
Yeah. Okay, thank you.
Hi, you mentioned how Tez can help optimize, the map and the reduce when it's HDFS, where you know the mapping of the data on HDFS. What about an external source like S3 or Azure Blob? Does that help there too?
So that depends on the APIs exposed by that file system. So HDFS actually exposes the API which gives you block locations. And that is the cornerstone of how you get locality with blocks.
So you're still using, the abstracted file system concepts of.
Correct. So there is a get block locations API there. If any file system is actually implementing that API, which gives us some idea of where the locations are, then we can use them. But if the file system doesn't expose that location hint because of whatever reason, then it's really not possible to make use of that.
All right, you guys are a shy bunch. I promise I won't eat you. I don't know what because, but I won't eat you. All right. Oh, good.
Actually, this is very interesting. The neat thing is if you look at the data system as a whole, not just a little piece of it, this touches the edge of not just the query optimizer, but if you add the right pieces in for things like GPUs, multi-tier, it touches on the edge of statistics for system-level query optimization. So if you thought that far out in terms of not just, well, I've got this section, and I've got a user who decided he wants to run Tez to get some performance, but instead to say, we're looking at tight integration with Yarn and possibly statistics across a larger system?
Absolutely. And in fact, like I said, the way we look at this is we want better throughput, we want shorter latencies, right? So if you look at the holistic picture, then just focusing on one aspect, this is one aspect of the runtime. It's great, we can make it fast, but you still have to, that's one of the reasons we've been working on things like ORC, which is a new file format. ORC gives us the right statistics at a block level and at a column level to make those optimization decisions. In future, you'll see us invest even more in things like adding stats to the Hive metastore or maybe edge catalog, so we can make even more sort of decisions upfront. Sort of the holy grail of getting a fast query is to do as little work as possible, right? It doesn't matter if you do a lot of work, but do it fast.
Well,
you're going to be slower.
The good news is, thinking about the previous speaker, if you get this one right, in the end, it shouldn't matter whether we're sitting on top of HDFS or incorporating Teradata or whatever. So now you can start to think at the enterprise level.
Exactly.
So neat stuff.
Thanks.
Quick question. I think you call them processors that form this DAG. How many processors are there? And how did you decide which ones to create?
So a processor needs to be defined by the user, and each user has their own unique set of tasks or processing that they want to run. Currently, we have two processors. One is the map processor, and the other is the reduce processor, which maps to the actual existing mappers and reducers so that they can integrate with Tez. But we'll soon be working on a generic N input, N output processor, so that unlocks a few more of these things. But in general, if you have a specific use case, there will be a set of generic operators which you can plug into. But if you have a very specific use case, you're welcome to write your own processor. So there's actually no limit to the number of processors you can write. The idea is that in some time, as people write their own processors, we will have a composable set of processors that people can use and build on top of. For example, somebody will write a sort processor. And in fact, people will write multiple versions of sort operators which are optimized for different workloads. And you can pick and choose your operator based on what exactly you're trying to solve.
Okay, and this annotations work that you mentioned, will it automatically figure out how people's contributions are composable?
Right, so we need to figure, we're still not there, but we need to figure out annotations. A simple example of annotation is whether this processor works on, what kind of data model this processor works on. Is it key value or is it tuple? You can only compose the key value processor with another key value processor. These kind of annotations we still are in the process of working out, so that today you can, as a human being, you can, when you're configuring your Tez task, you can configure two processors because you know what they are. But if you want to do it programmatically, you'll need these annotations so that semantically you can do this checking in code rather than in your head. So we are still in the process of figuring out a correct set of annotations so that we know that two sets of processors or input outputs can match semantically and work with each other.
Thank you.
And it's not just it's not just key value or tuple, right? You might want to add semantics to your keys and values. I mean, so there's actually a great paper called the PACT paper, which talks about parallelization constructs. So PACT paper talks about how you can put semantics on your incoming data and then have processors which take advantage of the semantics. So for example, one of the semantics is it's fully ordered. Another semantic is it's grouped. It's not sorted, but grouped. You can make all these smart decisions based on the annotations coming in. But again, it's sort of early days for that yet. All right, cool. Thanks, guys.
Thank you.